We will not go into the derivation of these vector identities. Okay. The first one, divergence of sum of two vectors is equal to divergence of A plus divergence of B. Okay, simple. Second one, curl of sum of two vectors is equal to curl of A plus curl of B. Okay. Third one, if f is a differentiable vector function and phi is a differentiable scalar function, then divergence of phi f is equal to gradient of phi dot A plus phi divergence A. See, divergence is nothing but delta dot phi f. Okay, so this will be f plus phi delta dot A. Okay, simple. Similarly, in this only, if I write in terms of curl of phi f, this will become gradient of phi cross product with function, sorry, uh, in the previous thing, though I have written here A, it is not F, A, it will be F. Cross product with function F plus phi, now finding the curl of F. Okay, so this is the thing, the two important properties related to divergence and curl, while both scalar function and vector functions are involved. Fourth one, divergence of two vector A cross B, where A cross B is a cross product of it, is equal to B dot curl A minus A dot curl B. Okay, curl of A minus A dot curl of B. So fourth vector identity. Fifth one, curl of cross product of two vectors A and B is equal to, this is a little bigger, A minus E divergence A plus A divergence. We have to remember these vector identities. In the exam, there is no derivation to be asked. Okay, so we should remember these vector identities. Sixth one, gradient of A dot B. Generally, gradient is defined for scalar function. So we cannot have a gradient for A cross B, but we'll have gradient for A dot B, because A cross B will give me a vector quantity. Okay, for that we cannot find the gradient. We will find the gradient only for the scalar functions. A dot B is a scalar quantity, because cross product dot product of two vectors is scalar. A B plus B into curl of A plus A into curl of. Okay, this is property number 6. Seventh one, divergence of gradient of a scalar function phi is equal to delta square phi. Okay, see, this is nothing but delta dot delta phi. For delta, I can write I of delta by del x plus j of delta by del y plus k of delta by del z dot delta by del x phi I can plus delta by del y phi j cap plus delta by del z phi k cap. So this can be written as delta square by delta x square phi plus delta square by delta y square phi plus delta square delta z square phi. Okay, this way it is derived. It will become delta square phi. This is a very important one. Earlier one was property number 7. Now 8th one. Curve of the gradient of phi is 0. That means curve of gradient of phi is equal to 0. Okay, how to prove this? Just simply write the basic steps. Del by del x plus j times of del by del y plus k times of del by del z. This is a cross product with del phi by del x I plus del phi by del y j plus del phi by del z k. Now write this matrix I j k delta by delta x delta by delta y delta by delta z. This will be del phi by del x del phi by del y del phi by del z. Okay, on solving this I will get 0. Okay, simple. Ninth property, divergence of curl of vector A is equal to 0. That means delta del dot del cross A is equal to 0. It can be proved in a similar way. Okay, curl of A is equal to gradient of divergence A minus del square. It's important one. This is used generally in while solving for lattice equation also. Okay. Now we will see few problems based on these identities. First one. Find divergence of r to the power n r. Okay. R to the power n is a scalar function. R is a vector function. Okay. So if you look at the solution, it is nothing but divergence of phi a. Okay. So the identity which we have to use for this is phi divergence a plus a dot gradient phi. Now I can write this as r to the power n divergence r plus r dot gradient of r to the power n. Now divergence of r is equal to del by del x I plus del by del z del y j plus del by del z k dot product with xi plus yj plus zk is equal to 3. Okay. Gradient of r to the power n is equal to n r to the power n minus 1 1 by r capital. Okay. So this divergence of phi a can be written as 3 r to the power n plus vector r dot n r to the power n minus 1 1 by scalar function r multiplied by vector r. Okay. So this can be written as 3 r to the power n plus n r n minus 2 r dot r. This again can be written as 3 r to the power n plus n r n minus 2 r square. So this is 3 plus n r to the power n. Okay. So this is one problem which can be solved using properties. To this problem, just one note. Delta square r to the power n r is equal to n plus 3 r n minus 2 r. This r is a vector function. This is a scalar function. Okay. Simple use of property, how it helps in solving a problem. Now Let's see what is directional derivative. We'll come to the problems related to identities further in this topic. What is directional derivatives and how to find the directional derivative. Okay. We know that we just remember this point that gradient f is a vector normal to surface f. Okay, and it is equal to a constant and has a magnitude equal to rate of change of f along the normal. That means if any surface is there by f, and if I find delta f for this surface, then delta f will be normal to that surface at that particular point P. Okay, so it will always be a normal to that. Now directional derivative is finding the dot product of this delta f, sorry, gradient f dot product with the given vector will give me the directional derivative of this. Okay, so this directional derivative can be found by first finding the gradient of a function and then finding the cross product of that gradient of function with the given vector. Okay, so we will see the problems. Find the unit vector normal to the surface. Suppose a function f is given as x y cube z square minus 4. Find unit vector normal to surface f at point minus 1 comma minus 1 comma 2. Okay, so solution. If we are saying find the unit vector normal, so first when we are finding the normal vector, that means you have to find the gradient of that. So you have to find delta f. This will be I times of delta by delta x y cube z square minus 4 plus j times of delta by delta y x y cube z square minus 4 plus k times of delta by delta z x y cube z square minus 4. On solving this, we will get I cap y cube z square plus j cap 3xy square z square plus k cap 2x y cube z. Okay, so this is a gradient of f at point minus 1 comma minus 1 comma 2. We have to substitute x y z with these points. So I will get a normal vector which is equal to minus 4i minus 12j plus 4j. Substituting this point here, okay, I'll get this vector. This is not a normal vector. For finding the normal vector, again I have to divide this by its magnitude. Minus 4i minus 12j plus 4k divided by under root of minus 4 square minus 12 square plus 4 square. Okay, this gives me the final unit vector normal to the surface f. Okay, understood how to solve the problem? So simple to find the gradient f, and then finding the gradient f, substitute the given points in the given gradient f, and then divide by the magnitude for getting the unit vector normal to that surface. So the previous problem was related to finding the unit vector normal to a surface. Now we will find how to find the directional derivative. Okay. For a given function f, it can be treated as a surface equal to x y square plus y z cube. Find directional derivative at point 2 comma minus 1 comma 1 in the direction of I plus 2j plus 2k. Okay. Now the procedure of finding a unit a gradient f will remain the same. After that we have to find the dot product delta f. Y square plus yz cube plus y square plus yz cube plus k times of delta by delta y delta by delta z x y square plus y z cube. I will get I cap y square plus j cap 2x y plus z cube plus k cap 3y z square. Okay. On substituting the point 2 comma minus 1 comma 1 in the given gradient, I'll get delta f is equal to I minus 3j minus 3. Okay. So now this is the gradient of f. Now directional derivative is equal to delta f dot given vector I plus 2j plus 2k, its magnitude 1 plus 4 plus 4. Okay, so I will get something like I minus 3j minus 3k I plus 2j plus 2k upon 9. This is equal to 1 minus 6 minus 6 by 3 minus 11 by 3. So this is a directional derivative of a given function at the point in the direction of the given vector. Okay, so this is a procedure for finding the directional derivative. It is a simple procedure. Okay, Now this gradient problem can be asked in different way also. For example, see this problem. Suppose a question comes to find the greatest rate of increase. To find the greatest rate of increase. It means that for this we have to find the gradient. Okay. Now question is to find the greatest rate of increase of function f, which is equal to x square plus yz square at point 1 comma minus 1 comma 3. Okay. F is given, we have to find delta f. Del by del x, x square plus yz square I cap plus del by del y, x square plus yz square j cap plus del by del z, x square plus yz square j cap. Okay. Now on solving this I will get 2x I plus z square j cap plus 2yz j cap. This is my gradient of f. Okay. To find the greatest rate of increase at point 1 comma minus 1 comma 3, I have to substitute this point in this gradient f. I will get 2 into 1 I cap plus 9 j cap minus 2 into 1 into 3 k cap. So this is nothing but 2 I cap plus 9 j cap minus 6 k cap. So this is the greatest rate of increase of a function at the point 1 comma minus 1 comma 3. Okay. So this solves the few basic problems related to directional derivatives and to finding the gradient. Okay.